All right, well, if there are no other questions, then we're going to get started on 4.7. If you have a scientific calculator, I think that's probably a good thing for today because we're going to be computing a lot of numbers. And if you happen to have your formula sheet with area and volume stuff that you made for exam 3, that actually might be pretty handy today as well, because we'll be using some of those formulas. All right, so we're going to get started with 4.7. All right, so 4.7 is called applied optimization problems. All right, applied optimization problem. Now, your textbook gives you a list of steps that you can kind of take to help with the problem solving. I would say that this unit is most similar to related rates, in the sense that there's kind of like a flow that you use for every problem, but the formulas that you use are going to be different. The graphs that you might need might be different. And so a lot of this goes back to being able to draw a diagram and come up with the proper equations for area and volume or whatever it might be, and use those to help you solve the problem, okay? Now, some of you are probably like, oh, shoot, that sounds terrible. But it is definitely an exercise in problem-solving strategies. And this particular topic comes up again in Calc 3. So those of you who are in it for the long haul, Calc 3, you'll have a second chance to take a look at this. However, you're going to be learning how to do it in a different way. So it is important that you have at least some understanding of it now, so that when you see it again in 2 classes, that you'll be able to build on that knowledge. All right, so let's read through the problem-solving strategies here, and I'm going to kind of follow them loosely, but I'll try and make my steps explicit. And again, I encourage you to ask questions as we're going along. So, step 1, they say introduce all variables. If applicable, draw a figure and label all variables. Now, I am really big into this part, drawing a figure and labeling all the variables, because I feel like for me, I'm definitely a visual learner. And so seeing what it looks like helps me figure out, all right, which equations might I need, what information do I have, and what information do I need. All right, step 2 says determine which quantity is to be maximized or minimized. So that's really what we're going to be looking at here, whether things have a maximum or a minimum, okay? And if you read through the questions, every single question is going to say, find the maximum this, or find the minimum this. Step 3, write a formula for the quantity to be maximized or minimized in terms of the variables. The formula may involve more than one variable. And so this more than one variable situation, that's what you're going to learn how to handle in Calc 3. So sometimes people call Calc 3 multivariable calculus because you study how to answer these problems with more than one variable. However, we are in Calc 1, which is often called single variable calculus. So we're going to learn another way to deal with having more than one variable, okay? Step 4, write any equations relating to the independent variables in the formula from step 3. Use these equations to write the quantity to be maximized or minimized as a function of one variable. So this is really what we're looking for. We want to be able to write a function with only one variable. And the last 2 steps, we're going to identify the domain of consideration based on the physical problem. And then step 6, we're going to locate the maximum or minimum value. Now, we've read this word maximum and minimum a lot, and I just want to draw a little picture up in this corner before we get started. So if I have a maximum point on a graph, someone tell me about the slope on this side. Slope is positive, negative, or 0?
Positive.
Positive, good. All right, what about the slope on this side?
Negative.
Negative, all right. And what about this slope right at the very tip top?
0.
0, good, okay. So this has a slope of 0 at the maximum point, okay? Now, if I were to squeeze a separate picture in here and have a situation where I have a minimum point, I bet you could all tell me that the slope on the left-hand side is negative, and that the slope on the right-hand side is positive, and that the slope right at the bottom is gonna be 0, okay? So what's another way for me to say slope?
Change of rate.
Rate of change. I would say, yeah, rate of change could be one. What's another way to say slope?
Rise over run.
Rise over run, sure. And these were answers that I think we all knew before we got to calculus, but what have we learned in this class about how to describe slope?
It's a tangent line.
It is the tangent line. Yes, we can determine slope from a tangent line. And how do we find the equation of the tangent line?
Derivative?
Derivatives, yeah. So all of these, and our slope equals 0, our slope equals 0. Really what we're looking for is a application of derivatives. Whoa. Okay. So when I say that the slope at a maximum or minimum is 0, what I'm also saying is that the derivative at a maximum or minimum is 0. Okay, now this is going to be super fundamental to every one of these problems that we're solving. At some point, we're going to take a derivative and we're going to set it equal to 0. So if you are doing these problems on your own and you don't take a derivative and you don't set something equal to 0, something went wrong, like way wrong, okay? So at some point in every one of these 4.7 problems, we're going to find a derivative, we're going to set it equal to 0. All right, so let's go ahead and get started. So for those of you who were in my 141 class, some of these problems should actually look pretty familiar, but hopefully they'll look a little less scary than they did the first time, okay? So let's take a look at example 1. Example 1 says a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides, all right? Quick check for you. How many sides does this garden have?
Four.
Garden has 4 sides. How many sides do we need a fence on?
3.
3. Okay, so we need 4 sides for the garden to fully enclose it, but only 3 of the sides are going to have fence on them. All right, so I have wire fencing for the other 3 sides. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. Then determine the maximum area. So there it is. We want to find the maximum area, all right? So if we kind of think back to our little pictures in the corner, we want to picture like the one on the left where we have a top of a bump, and we want to find out exactly where the top of the bump is. And instead of just graphing it and using algebra, we're going to say, let's write an equation for that picture. And then when we take the derivative and set the slope equal to 0, that will tell us exactly where that point is. All right, so we're gonna start off with a diagram, okay? That is one of my sort of go-to strategies when I work through these problems is I'm gonna start with a diagram. So step 1, we're gonna draw a diagram. So I'm gonna say that I have a rock wall, okay? So this part is the rock wall. So this is one side of my garden. This is the side that does not need fence because there's a rock wall there. So I don't need to use my 100 feet along this particular side. Now I'm gonna draw the rest of my garden. So I have this side, I have this side, and I have this side. And so my garden is gonna be everything that is inside of that rectangle. And everything in the purple is gonna be wire fencing. All right, so this is a good visual of why we only need fence for 3 sides and not all 4 sides. Now we're gonna go ahead and label this with some variables. Now I'm not super creative, so anything that's horizontal, I usually give an X, and anything that has vertical, I usually call a Y. All right, so I know that that horizontal distance across the top is X, and then the 2 on the side are both Y because it's a rectangle, so the left side is gonna be the same length as the right side. Okay, so got my diagram. Now what I'm gonna do is I'm gonna go ahead and write the equation of what I want to maximize, okay? So when I go back in the question, it says determine the dimensions that would create a garden of maximum area. So this maximum area means I want to write an area equation. So area of a rectangle is going to be X times Y, or length times width. When I look at the left-hand side, I notice that I have an X and I have a Y. And this is exactly what I mean by a formula may involve more than one variable. So I have an X and a Y together on one side, and that's what you'll learn how to handle in Calc 3, but we need to come up with a different strategy to figure out how to get rid of one of those letters. All right, so I've written my equation. Now let's write a note to ourselves that we want to find the derivative of the area. And in order to do that, we need to get rid of X or Y. Like one of those variables needs to go. Either my equation is going to have only X's or my equation is only going to have Y's. I'm going to pause here for just a brief moment. Are there any questions so far on the setup? Okay. So this next part is really important. How do we get rid of X or Y? And the answer is usually whatever you did in step 1 is going to help you with step 2. Okay, so let's go back to step 1 for a moment. Now, step 1, I said everything in the purple is wire fencing. And I know that I have 100 feet of wire fence. and that is going to go everywhere that I see the purple. So it's going to be y plus x plus y. So y plus x plus y equals 100. And then I'm going to go ahead and combine some like terms. So I get 2y plus x equals 100. And then I kind of have a choice here. Do I want to get the x by itself, or do I want to get the y by itself? All right. And I'm going to show you both ways right now. So if I give the x by itself, I'm going to get x equals 100 minus 2y. Does that make sense to folks? I'm just subtracting that 2y.
Yes.
Yeah, okay. Now let's say I wanted to get y by itself. Well, I'd have to do 100 minus x equals 2y, and then I'd have to divide by 2. So I could do either one. One of them, though, looks a little bit easier to work with than the other. So to me, the first one I did was easier for 2 reasons. One, I only had to subtract the 2y. That I can do. So it was only one step. The second one to me is harder for 2 reasons. It was 2 steps, but also I'm going to end up with some sort of fractions here. And I'd really rather not deal with fractions if I don't have to. So for those 2 reasons, I'm going to go ahead and use this one and not this one. Okay. You can use either one and you will still get the right answer, but one of those versions is going to cause more work for you than the other. All right. So let's see how this helps us. Well, I know in my area equation, I have area equals x times y, which means that everywhere I see x, been doing that a lot lately, everywhere I see an x, I can replace it with 100 minus 2y. So in my equation, I'm going to get not x times y, but 100 minus 2y times y. Does that substitution make sense to folks?
Yes.
Yes, okay. All right, so that's step 1 and step 2. Step 1 is draw a diagram. Step 2 is write the equation that you want to take the derivative of. And then sometimes you need to go back to step 1 and use that information to help you create a single variable equation. Now, once you've got your single variable equation, okay, now we can move on to step 3. So in step 3, we're going to simplify if we can, and then we're going to take a derivative. What do we do after we take the derivative?
Set it equal to 0.
Set it equal to 0. And the reason why, again, is because I'm looking for the maximum area, and I know that the slope at the maximum is 0, or the derivative at the maximum is equal to 0. All right. So, ideas on how to simplify my equation before I take a derivative.
Just multiply it out.
Yeah, multiply it out. So I'm going to take the y and I'm going to multiply it in. And so I'll get 100y minus 2y squared. All right. Now that I've simplified, that means I don't have to use the product rule, right? That's pretty nice. I don't have to use the product rule when I'm taking the derivative because I distributed it, so I don't have to worry about that. Now when I take my derivative, I'm going to get dA over what's going to be on the bottom here?
dy.
dy, good, because that's the variable on the other side, okay? And let's take our derivative. What's the derivative of 100y?
100.
What is it?
100.
100, yeah. And derivative of 2y squared?
4y.
4y, beautiful. All right, so I've taken my derivative and I'm gonna set it equal to 0. 100 minus 4y. Okay. So after you take your derivative and set it equal to 0, you're gonna solve for your variable. All right. So in this case, I'm gonna get 100 equals 4y, because I'm gonna add the 4y to both sides. And then my last step is just to divide by 4. So I'll get y equals 25. I think we're looking at 25 feet here. Okay. So let's go back to the question and make sure that we've answered it in its entirety. So it says, given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. So in order to answer the question, I need y, but I also need x. X and y together will give me the dimensions. I found my y. How do I find my x?
Just substitute it back.
Yeah,
Minus 2y.
into which one?
100 minus 2y.
Yeah, I'm gonna take this 25 and I'm gonna plug it back into this purple equation up here. Exactly. Okay, so let's kind of call this maybe step 4, where we answer all the parts of the question. So I know y equals 25 feet. I know x is gonna equal 100 minus 2 times 25. And that's gonna give me 50 feet. All right, so I've got dimensions of 25 feet by 50 feet. And then I go back to the question and just make sure I've answered everything. There's a last part that says, then determine the maximum area. So they want me to find the area. And which equation can I use to help me find the area here?
X times y.
X times y, yeah. So I'm going to take 25 times 50, and when I multiply that out, I should get 1250 feet squared. All right. So this is our first example of optimization, okay? Now, one thing that I want to do, and I'll do this in the different color, I'm going to squeeze a little diagram in the middle of how this relates to the pictures that I was sort of drawing above. So if you were to take this equation, and I said, what shape is that equation? I hope that we would be able to know that it's a parabola, because it's a y squared. And more significantly, because of the minus in front of that y squared, we would know it's an upside down parabola. And so if you were to graph this on Desmos, you would get some sort of upside down parabola, okay? And when you look for the maximum point, you're gonna get a coordinate. And that coordinate is gonna be y, comma, a. Because y is like my x and a is like my y. And the number that you would get for y, you would get 25, and then the a would be 1250. Okay, so this in the pink right here is one way that you can check your answers as you're doing some of the practice problems, just to make sure that you got the right answer. All right, as long as you get that beginning equation right, you're able to graph it and kind of see where the maximum or the minimum point is. All right, so any questions so far on number 1? Okay. Well, we're going to go ahead and move on to example number 2 then. Okay. So example number 1 is a pretty classic kind of problem, meaning like it comes up a lot, all right? And same thing with example number 2. I tried to pick questions that were more like common questions rather than like the ones that are sort of way out there, because I think it's important that we're able to handle a lot of these sort of common cases, all right? So for this one, let's go ahead and read through the problem. So example number 2 says an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. What size square should be cut out of each corner to get a box with the maximum volume? What is the maximum volume? So immediately I'm cued into this maximum volume, okay? And I know that when I get to step 2, I better be writing a volume equation. And when I get to step 3, I'm gonna take the derivative of that volume equation and I'm gonna set it equal to 0. Okay, so let's focus on our step 1 for right now. So step 1. All right, so for step 1, I'm going to draw a diagram. And so I'm going to start with this flat piece of cardboard. Okay, and I'm going to label it with the 24 inches by 36 inches. So I know that this bottom length, that one looks a little bit longer, so I'll call that the 36 inches. And then the one that's going up and down for me is 24 inches. Okay. So I have a 24 by 36 inch piece of cardboard. And now I'm going to remove a square from each corner of the box. Okay. So that means that I'm going to take a box cutter or some scissors and I'm going to cut a little corner out, a little square out from each corner. Okay. And I don't know how big I want to cut these squares. I could make them really big or I could make them really small squares. But either way, when I fold them up or when I cut them out, I'm going to be left with a shape kind of like this. So this second picture is like the green squares are gone. I cut them out. And then what I'm going to do is I'm going to crease right along here. I'm going to fold that side up. I'm going to crease here. I'm going to crease here. And I'm going to crease here. And when I fold them up, I should end up with a box. Okay, so when I fold up the edges, I'm going to end up with a box. Now they say specifically that this is an open top box, meaning it's like a shoe box, but you took the lid off. Or it's like those storage containers, but you took the lid off. Okay, so there's no top to this box. There's only a bottom and 4 sides. All right, any questions on the diagram so far? Okay. So let's move on to step 2 then. Step 2, this is where we write our volume equation, okay? Or the equation of the thing that we're maximizing. So I know that the volume of a box is going to be length times width times height. Okay, so that's something to remember from geometry, that the volume of a box is length times width times height. Now, This one has way too many letters. I have 3 letters on this side. I don't want that many. So this is what I need to do. I need to get 3 letters, 3 different letters to just be 1 letter. Okay, so either I'm going to have L or W or H. Okay. So let's go back to our diagram to help us figure out how to do this. Well, this part that I cut out, okay, on this diagram, that would be like this part. Would you guys agree that like this corner is the same as the other corner that's shaded green?
Yeah.
Yeah, okay. When you fold the edges up, it should become this edge. Okay, so the square that I cut out, once I got rid of it, the size that the square is actually tells me how tall the box is going to be. So the bigger the square, the taller the box. The shorter the square, or the smaller the square, the shorter the box. So I'm going to go ahead and say that the size of the square that I cut out, I'm going to call this X by X. That means that I have X and X over here, and then this green line at the end means that the box has a height of X. So I'm going to take my H and I'm going to replace that with an X, all right? X is going to be the height of my box. Now, if I cut X out here and I cut it out here, how long is this section that's left?
-36 minus 2x.
36 minus 2x. Okay, why do you say minus 2x?
You got 1 on each side.
You got 1 on each side, exactly. Okay, what could we say about this length right here?
24 minus 2x.
24 minus 2x. Good, because I'm cutting out 1 square from each side. So this part of the box is going to be 24 minus 2x. And this part of the box is going to be 36 minus 2x. So now I can write the entire volume equation in terms of x. So for length, we'll say 36 minus 2x. For the width, we'll say 24 minus 2x. And for the height, we'll just say x. All right. Questions on how we got the formula to all be in terms of x? Okay. So now we have the equation. It only has a single variable, x, and now I'm ready to simplify and take the derivative and set it equal to 0. So I'm going to rewrite my equation here. 36 minus 2x times 24 minus 2x times x. And I'm going to go ahead and FOIL these two, and then I will take care of I'll distribute the x in at the very end. So 36 times 24 is going to give me 864, right? My outer terms will be 36 times -2 minus 2 times 24. So I get negative 72 minus 48, which is minus 120x. And then my last terms multiply to make a positive 4x squared. And I still have that x on the end. And now I'm going to distribute this x into all three terms. And I'm going to get 864x minus 120x squared plus 4x cubed. All right, so from here, let's go ahead and take our derivative. So dv dx is going to be the derivative of 864x is 864. What's the derivative of the second term?
$240x.
Minus 240x, good. And then the derivative of the last term?
12x squared.
Good. All right. So there are lots of things that are trickier about optimization problems, but the one nice thing is that the derivative part tends to be super easy. Okay, so like we're really just using a lot of power rule. We just want to make sure that we're doing it correctly. All right, so now I've got my derivative. Now I can set this equal to 0. So I'm going to say that this equals 0. Let's do this. So in order to solve this quadratic, okay, because I have 12x squared minus 240x plus 864, I'm going to see if I can find a greatest common factor for all these terms so that I can work with some smaller numbers instead. So I notice that 12 goes into every single term on the left-hand side. So what I can say is that 12, I'm going to factor that out, x squared, okay, and then 240 divided by 12 is 20, so minus 20x. And then 864 divided by 12 is 72, so plus 72 equals 0. I would really encourage you to find a greatest common factor if there is one, because now if it's not factorable, it just makes your life so much easier to work with smaller numbers when you're using the quadratic formula, okay? So in this case, this is not factorable. So we're going to go ahead and use quadratic formula to solve for our x's. So in this case, my a is 1, my b is negative 20, and my c is 72. All right, so let's solve. X equals negative 20 plus or minus the square root of negative 20 squared minus 4 times 1 times 72 all over 2. And this is going to give me 20 plus or minus. Let's see what we get on the inside. 20 squared is going to be 400 minus 4 times 72 is going to give me 112 on the inside. Okay. And let's see if we can simplify this more. So I have 20 plus or minus, let's see, 112 divided by 16. 16 goes into it, so I have a 4 root 7 over 2. And then I could say that x is either 10 plus or minus 2 root 7. All right, so I've got two options here. 10 plus 2 root 7 or 10 minus 2 root 7. Those are two possible points for a maximum of this volume equation. Now, what we need to do is make sure, if we go back to our diagram, so I showed an example where I sort of cut out a reasonable x. But if I go back to my diagram and I kind of redraw another cardboard piece, and I'm not thinking super clearly, and I just start cutting, and I cut a square this big out of one corner, can I cut squares of that same size out of every other corner?
No.
No, because it's taken up too much space already. I've already overcut. Funny side story, when we were little and I had to take home ec, my sister had to take home ec, and one of the classes, or one of the projects they did was like sewing a stuffed animal. But it was like this kit where you like the school orders the stuffed animal, and then you just like follow the pattern, you cut it and you sew it and you stuff it. But my mom had to buy my sister 3 of them because she kept cutting too much off of the pattern. So like her poor bear didn't have like one ear, and then it was like missing a whole leg. And I think she finally got it right at the end. But my mom was pretty upset about having to buy more than one. So when you're cutting, you really want to think about what makes sense for the problem. So there is such a thing as cutting out too big of a square in one corner. And so it turns out that of our two options below, that this 10 minus 2 root 7 and this 10 plus 2 root 7, this 10 plus 2 root 7 is actually too big of a square to cut out. And here's how you can check that. You can take this number and plug it back into your volume equation. If you get a negative number, that is a big sign that that number doesn't work, because you can't have negative volume. But if you plug in this number, okay, that number does work. And so what we can say now is we have two answers, but one of them does not represent the maximum volume. And so what we need to do now is we know that this is the length of the square. So let's turn that maybe momentarily into a decimal to help us envision like what we're actually cutting out. So if I turn this into a decimal, I get that it's about 4.708 inches. Okay, and that seems kind of reasonable, but if I turn the other one into a decimal, this one is 15.29 inches. And if I look back at my diagram, one of the sides is only 24. There's no way I can cut 15 inches out of both sides and still have it work. Okay, so that's another way that you can tell that this one is too big, but this one is just right. All right, so let's read back at the question and make sure we've answered it now. So the question says, what size square should be cut out of each corner to get a box with the maximum volume? Well, our square should be 4.708 inches on all sides. So we've answered that part. Now, the next part of the question says, what is the maximum volume? So we need to take this 4.708 and we need to plug it back in to our volume equation. You can either plug it in here or you could plug it in here, your choice, okay? But take a moment to calculate that out, all right? And I'm gonna add our step 4 right in here. And I believe I'm getting a number kind of like this. Does that match what other folks are getting?
Yep.
Yeah, okay. Got at least one yes, that's good. Okay. So have I fully answered the question? Yes, I've got the dimensions of the square and I've got the maximum volume. Okay. So even though this is a totally different scenario than example number 1, we did kind of follow the same steps, which is draw and label a diagram, come up with your equation, use your diagram and other information to help you make a single variable equation. And then from there, we take our derivative, we set it equal to 0, and we solve. All right, so let's do this. Let's go ahead and do one more question, and then we'll take a break. All right, so let's take a look at question number 3. All right. So I think for some folks like myself, like I really enjoy the different types of problems that are out there. I know there are some of you who wish that they would just all be the same kind of problem, but ultimately that gets a little bit boring. And I think that for some of us, we're never really gonna think, okay, I'm building this garden in my backyard. How am I going to maximize the area of this garden? Like you'll probably just go out and buy more fence if you want more fence. Or like in example number 2, you're probably just going to not make your own box, but like have a box that's already made. So sometimes these situations feel very contrived, but they actually have a lot of applications to biology. They actually have a lot of applications to business. So that's why a lot of business, if you're thinking about being a business major, they do require you to take a different calculus, which is more focused on like an example like number 3, okay? So let's take a look at example number 3. So it says owners of a car rental company have determined that they charge their customers P dollars per day. So that means that they would charge them anywhere between $60 and $150. It has found that the number of cars rented per day can be modeled by this function, N of P equals 750 minus 5P. How much should the company charge each customer to maximize the revenue? So this is maybe a little bit more important for some of us when we think about wanting to maximize our income on certain things. So if you've ever thought about crafting things, or creating things, you want to make sure that you sell it at a price where you're going to be able to make the most amount of money. And that doesn't necessarily mean charging more for it, because at some point folks will be like, I'm not paying $100 for this one small thing. And on the flip side, if you charge too little, people might be like, I don't trust the quality of your product, or you might not be making enough money. So there is a sweet spot, this maximum revenue place, where we can say that you're gonna make the most amount of money. All right, so let's start off with step 1. Now we're not gonna draw a diagram for this one because this you don't need to, like, drawing a car won't help you answer the problem. All right, but we'll use step 1 to talk about a little bit of background, okay? So this word revenue is effectively looking at your income, okay? And if you look into more businessy applications, you do look at cost, and then revenue and cost will help you figure out your profit, right? So revenue is different from profit. This is not saying like after you've paid your rent and after you've paid your employees, how much are you making? Revenue is just how much you're making, okay? So revenue is going to be the same as income. So in order to find the revenue, I'm going to call that R of P. I can take the cost per car and I multiply it by the number of cars rented. All right, so let's think about that for a moment. If I charge $100 per car and I rent one car, I make $100, or I have income of $100. If I rent a car for $100 and I rent 10 cars, I'm going to make $1,000. Okay, so in order to find my income, I'm going to take the cost of each item and I'm going to multiply it by the number of items that I sell or that I rent. Now we can think about using the information from the problem to fill in the different parts. So they say that the car rental company charges its customers P dollars per day. So this cost per car is P. And then the number of cars rented is that linear function they gave us, 750 minus 5P. All right, and what am I doing to those two? I'm multiplying them. So I've actually already got this with a single variable. All right, I only have the variable P, or the cost per day of the car. I don't have any other variables, so I don't have to substitute anything out like I did in example 1 and example 2. So from here, I'm actually ready to go into step 3. So my equation is P parentheses 750 minus 5P. All right. And someone mentioned earlier that when we see something like this, in terms of simplifying, it's probably best to distribute. So we don't need to use the product rule. So we could say R of P equals 750P minus 5P squared. Now, what shape is this revenue curve?
Downward facing parabola.
It is a downward facing parabola, exactly, because we have the negative and we have that squared. So if I kind of think ahead a little bit, and I know that I'm going to have I could go back and check my answer by graphing this. I know I'm going to have a parabola, and I know at the vertex, the coordinates will be the cost, comma, the revenue. So whatever number I get for P after I take the derivative, set it equal to 0 and solve, that will give me the cost that I should charge the customer. Okay, so let's go ahead and find our derivative. So dr dp is going to be 750 minus 10p. And I'm going to set this equal to 0 because I know, and you know, that at a maximum, the slope or the derivative is going to be 0. And now I'm going to add 10p to both sides. And it turns out that if I charge customers $75, then I'm going to maximize my revenue. So the x coordinate on my graph should be 75. All right. Now, it does not ask you to find the revenue here, But if you did want to find the revenue, how would you find it?
Would you plug P back into the original equation?
Plug 75 into the initial revenue equation.
Yeah, we're gonna go back to our original and we're gonna find R of 75, which will be 750 times 75 minus 5 times 75 squared minus, and I believe we get a revenue of just over 28,000. Okay, so this is a little bit more of a like practical application for folks who are like, I just don't understand why we have to do all the other complicated stuff. But again, it gives us just another tool to find maximum and minimum points. All right. So let's take a short break. Let's be back at 10:47. All right, 10:47. And Diana, if you want to pause the video, that would be awesome. But let's be back.
It started already.
Awesome, thank you. All right, folks, so we're going to go back into our 4.7 practice and finish up as much as we can today. All right, so let's take a look at question number 4. Yeah, question number 4. Okay, so question number 4 says that a rectangular box with a square base, an open top, and a volume of 216 cubic inches is to be constructed. What should the dimensions of the box be to minimize the surface area of the box? What is the minimum surface area? So let's go ahead and get started with a diagram. So step 1. Now, when it says a rectangular box with a square base, the first kind of visual that comes to mind for me is, you know, they have like sort of those like long Kleenex boxes, and then they have like the smaller ones that you can put by your bed. They're like this, they're like square boxes, but they're actually a little taller than they are square. That's kind of what they mean by a rectangular box with a square base. Okay, but kind of like the last problem, there is no top to this box. So how many sides does this box have?
5.
5. Yes, it has 5. All right, so let's draw a rectangular box. Okay, and we know that the base is square, so like these two sides are the same. And we know that the height of this box is going to be different because it's a rectangle, okay? So those two are the same, but this one, the height of the box is going to be different. Now, it says, what should the dimensions of the box be to minimize the surface area of the box? So immediately I'm cueing in to where it says minimize the surface area, and that's what I'm going to write an equation for in step 2. Okay, so I'm going to need to find an equation that talks about the surface area of this box. Now, you guys know that it only has 5 sides, so that should be helpful in getting us started, okay? But if I think about the surface area of this box, I know that there's the area of the base, all right? Plus, are the 4 sides of the box equal to each other, or are they different from each other?
Same.
Yeah, they are all going to be the same. And I have 4 sides. So I'm going to say 4 times the area of each side. Okay, so surface area is going to be area of the base plus 4 times the area of the side. Okay, now let's go back and label our diagram so that we can use some variables in our equation. So if I know that the base is a square, I can say that one side of the base is x and that the other side of the base is x. And that means I can say area of the base as x squared. Now let's call the height of the box y or some other letter. But what that tells me is that each of the 4 sides are going to have an area of x times y because they're rectangles. So I've got surface area equals x squared plus 4 times xy. Let's take a look. I have too many variables. I've got x squared, I've got x, but then I have this y, and that presence of the y means that it's a multivariable equation, and I want this to be a single variable equation. So I got to go back to my step 1, see if there's other information I missed in the problem originally, and think about how I can substitute that y away so that I only have x's. Or I could substitute the x's away and only have y's. So let's go back to our question. It says that this rectangular box with a square base has an open top and a volume of 216 cubic inches. So the volume of this box is 260 cubic inches. Now, using the variables in my diagram, what is an algebraic representation of the volume?
X times y.
X times y, exactly. That's our length times width times height. So I'm going to say x squared times y. Okay. Now, with this equation, just like last time, I have 2 options. I can isolate y or I can isolate x. So if I want to get y by itself, the only thing I need to do is take the 216 and divide it by the x squared. If I want to isolate the x, then I would divide the y away first. And then how do I get my x by itself here?
You square root it.
Yeah, you square root it. And already as I'm writing this, I'm like, I definitely don't want to use that one. Like if I'm thinking about derivatives, and this looks like a case where I have chain rule and then I have to have a fractional power. It's just more than I really want to do. Okay, it's not wrong to go about that part or about that way, but it might make your life way harder than it needs to be. And so for that reason, we're going to go ahead and substitute the y. And so what that means is that everywhere I see a y, I can replace it with 216 over x squared. So everywhere there's a y, I'm going to put 216 over x squared. So this is going to give me x squared plus 4 times x times 216 over x squared. Okay? And this equation is the one that I'm going to simplify, take the derivative of, and set it equal to 0. And that will help me find the dimensions of the base that will minimize the surface area. Okay. So step 3, let's simplify. So my surface area is x squared. That part's okay. What can I simplify in that second term though? Because I know fractions can be challenging for folks sometimes. So help me out. How do I simplify that second term?
Can you cross out an x from the 4 to an x squared?
Yes, you sure can. Yeah. So this x is really x over 1. So I can reduce it with one of the x's on the bottom. And then exactly, we can take the 4 and the 216 and multiply those. So 4 times 216 is 864. 864 is on the top. That x that you still have left is on the bottom. Now, because I know I'm taking a derivative, like I've already planned out that I'm going to take a derivative and set it equal to 0, it's probably better for me to write it like this. That way I can see the power and use the power rule.
I have a question.
For sure.
So do you not FOIL the 4 to the 4x? I mean, you did the 4x, but like you don't FOIL the 4 to the 4y?
Foiling only happens when you have this.
Oh, okay.
Yeah?
Okay.
Because 4 times x times y is the same as 4 times y times x. Like the order doesn't matter.
Oh, okay.
Okay. All right. So it looks like we're ready to take our derivative. So the derivative, and then that'll be dx on the bottom. Derivative of x squared is 2x minus 864x to the negative 2. Now again, I know that I'm going to be setting it equal to 0. So I'm going to go ahead and rewrite this as a fraction. Okay, there are benefits to using both forms, and that's why we spent so much time at the beginning of the year making sure we knew how to go back and forth between those two terms. All right, so let's take this, let's set it equal to 0. All right, now I don't love fractions, but I try and find a lot of workarounds, and this is one of those workarounds. I'm going to take the entire equation and I'm going to multiply by x squared. That's going to mean I distribute that here, I distribute that here, and I distribute that here. And I'm going to get 0 equals 2x cubed minus 864. Boom, no more fractions. Now, I'm going to add the 864 to both sides, and I'm going to divide by 2. So that's going to give me x cubed equals 432. Now, last step, I'm going to take the cube root. And that will give me x equals 7.559 inches.
Could you have just added the fraction to the other side, then cross multiplied?
For sure, yes.
Okay.
Yeah. I think I might do that in the video example, like this kind of question. I think I do that. So those are sort of two different strategies to work around.
Okay.
Okay. All right, so we get x equals 7.55 inches. So let's go back to our problem and make sure that we've answered everything we need to. We'll prep our step 4. So the question says, what should the dimensions of the box be? Well, that means I need an x and I need a y. And then it says, what is the minimum surface area? So I need to find my surface area. So I have x equals 7.559 inches. And a good thing I circled this in the red earlier, I can go ahead and use 216 over x squared to find my y. And that will give me a height of my rectangular box to be 3.780 inches. All right, so I've got my x and I've got my height of the box. And the last thing that I need to find is my surface area. And again, if you organize your work really well, all of the formulas are already there. You just have to find the right ones to plug it back into. So I'm going to take my x and I'm going to plug it into this equation. Okay. And so I'm going to get 7.559 squared plus 864 over 7.559. And that should give me 171.439 inches squared. All right. Any questions on example 4? All right. So let's move on to example 5. So we've got 2 more examples. And again, I tried to pick ones that were pretty like classic case questions. But if you like this kind of problem solving, there's like an endless variety of these kinds of problems, for better or for worse. All right, number 5. Also, this one actually out of all of them is probably the one that will get you the most bang for your buck when you get to Calc 3. Okay, this question definitely comes up again in a topic called Lagrange's multipliers, if you're interested in looking that up. But we're going to solve this question using what we know, which is single variable calculus, all right? And so that's a really good distinction to think about. Like when you're taking an exam, please make sure that you use strategies that we've gone over in class. Otherwise, it looks no suspicious. So example 5, a cylindrical can is to have a volume of 400 cubic centimeters. Find the dimensions, meaning the height and the radius of the can, so as to minimize its total surface area. Then determine the minimum surface area. All right, so let's start with a diagram. So we've got step 1, and we're gonna draw ourselves a cylinder. It's really important to know our vocabulary here too, right? Like we're not looking at an ice cream cone, that would be a cone. We're looking at a cylinder, so more like the ever elusive toilet paper tube, All right, so we've got a cylinder can. And this can has a volume of 400 cubic centimeters. Find the dimensions of the height and radius. So I know that the radius is like not all the way across the bottom, but halfway across the bottom. And I know that the height is how tall the can is. And what I want to do is to minimize the surface area. So a good sort of like real world example for this is if you think about all of the beverages that we purchase that come in aluminum cans. So for example, every once in a while, I like a Coke from the can, like I like it in the can better than the bottle. But when I get a can, sometimes I'm like, I don't want to finish all 12 ounces. And so when they came out with like the Coke minis or like the little ones that are in the 8-ounce cans, I was like, oh my gosh, this is so cute. Like I totally want to buy these. But it's important to think like if you're like a really environmentally friendly person, like what is the amount of waste that you're creating by using certain dimensions? It might mean that your can actually, even though it's smaller, uses more surface area per ounce than like the bigger cans. Okay, so that's sort of like the framing for this question. All right, so let's take a look at what our step 2 equation needs to be. So our step 2 equation is, they tell us right here, right? They want us to minimize the surface area. So our equation that we want to write in step 2, the one that we're going to simplify, take the derivative of, set it equal to 0, that is going to be the surface area of a can. And yes, you do need to know all of these formulas, okay? So with a can, I have a circle on the bottom and I have a circle on the top. So that's fair that I could say I have 2 circles. So 2 times area of a circle is pi r squared. Plus the part that wraps around the side of the can, so like the soup label part of a soup can, that area is 2 pi r h. All right. So let's look at our equation, single variable or multivariable, and I definitely see multivariable. I see an h in there. Everything would have been perfect if it was just r's. I could have then just taken my derivative, but I got that sneaky little h in there, so I have to get rid of one of the letters. I can either get rid of h or I can get rid of r, but let's go back to our initial question to see which one is going to be better. All right, volume formula for a cylindrical can. Someone tell me what that is.
By r squared h.
R squared h, good, because we've got the circles and we stack them up to a certain height, and that will give us the volume inside of the can. All right, so it looks like I have 2 options. I can, before we do that, sorry, we can say that these 2, because they're both equal to the volume, are actually equal to each other. So 400 equals pi r squared h. Now from here, I have 2 options. I can get the h by itself, or I can get the r by itself. So let's see. If I want to get h by itself, I'm just going to take the 400 and I'm going to divide away my pi r squared. Boom, done. Okay, one step, isolated. If I want to solve for my r, well, I'm going to get r squared equals 400 over pi h. And then, yeah, this is definitely one I don't want to use because look, I got this square root. I have a fraction on the inside. Like it's all kinds of stuff that we could do, but doesn't necessarily make sense when it's already so much work to do the rest of the problem. So we're going to take this one that we were able to isolate in one step, and bonus, it only has to go in one place. All right, there's only one h to sub in. That's it. So if we sub that in, we're going to get 2 pi r squared plus 2 pi r times 400 over pi r squared. And that is the surface area equation. That is a single variable. And now I can move on to step 3 where I simplify, take the derivative, set it equal to 0. All right, so 2 pi r squared is the first term. Take a moment and simplify that second term, and then someone tell me what you get.
Is it just 800 over r?
Let's see. So the pi and that pi go away, yeah. And then this r and one of the r's goes away. And then we can take that, and sure looks like you are correct, 800 over r. Good job. Okay. Now, again, I've pre-thought, like, what am I going to do with this equation? If I was just going to plug in a number, I wouldn't need to rewrite it. But I know I need to take a derivative. So I'm going to write it like this. Because now I can see the power, and now I can use the power rule. So I'll give you a moment to find the derivatives on the right-hand side. And then when you're done, if someone could share out what you get, that would be great.
I got 4 pi r minus 800 r to negative 2.
Perfect. Yeah. Bring down that 2. So 2 times 2 gives me 4 pi r. Good. Minus 800 r to the negative 2. Beautiful. Now again, thinking ahead, I know I want to set it equal to 0. So I'm going to go ahead and rewrite this as 800 over r squared. And now I'm going to set this equal to 0. 0 equals 4 pi r minus 800 over r squared. And let's do the other strategy that someone else mentioned, which is I'm going to add this to the other side, and then I'm going to cross multiply, okay? So I get 800 over r squared equals 4 pi r over 1. I cross multiply and I get 800 equals 4 pi r cubed. Now, if you did the same thing where you multiplied everything by r squared, you would get to the same answer, all right? So maybe later on, take a look back at these two questions and see sort of like what your preference is and how you're gonna minimize your own mistakes, okay? Now from here, r cubed is going to be 800 over 4 pi. And now I'm going to take the cube root. And let's turn that into a decimal. Just so we can kind of get an idea on the dimensions. And it looks like it is 3.993 And what are our units again? Centimeters. Centimeters for the radius. Okay. So let's zoom back out for a moment and let's see what we have. So it says find the dimensions, the height and the radius of the can so as to minimize its total surface area. So I have the radius and now I just need to find the height. All right. So in step 4, I'm going to find the height and I'm going to determine the minimum surface area. So radius equals this. Height, I'm going to plug it into the equation I circled in the red above, 400 over pi times 3.993 squared. And that's going to get me 7.986 centimeters. So radius and height. All right, so radius and height are done, and now I need to find the surface area. So my surface area, I'm going to go ahead and plug it in to this equation right here. And so that's going to be 2 pi 3.993 squared plus 800 over 3.993. And let's see what we get when we type that all in. And you get a surface area of 300 centimeters squared. All right. Any questions about example number 5?
Professor,
Yes,
just real quick, could you scroll up to example 4 just to see the answer for surface area?
for sure.
Thank you.
You're welcome.
All right, you're good.
Okay, thank you.
Thanks.
All right, so folks, we have one last example to do here. Now, this is definitely one of those things that you might be like, oh yeah, this makes total sense when someone is talking me through it, but you need to do extra practice problems, okay? You really to take the time to like make sure this process feels really smooth for a variety of situations. All right, so again, there's that practice on Canvas that you can check out, and it has an answer key for written explanations as well as video explanations for each one, so you can kind of watch like one problem at a time. I know it can feel really overwhelming when the video is like long and you're like, oh my God, how many more problems are there? But this one is broken up, so each video is only one question. Please take the time this week to make sure you feel really solid on this, all right? If you leave all that studying to the last minute, the final exam is going to feel like a whole lot because it is cumulative, but we're also learning quite a bit of new information.
I have a question.
Yes.
So we just solved for surface area and everything. But how do we know it's the absolute minimum because we took the derivative?
Yes, so we know that it is the minimum if the volume of the can is 400 centimeters cubed.
Mm-hmm.
And so like if you graph this one, I think it looks something kind of like this shape. And the minimum point is like right here.
Okay.
Yeah. There is another branch to this equation, and I think it goes like this. But again, we're thinking about what's, like, we can't have a negative volume can. And so we don't even care about that branch, but we look at the branch that could actually give us an answer, and the point that we find is the minimum of that branch.
Okay.
Okay. All right. So last question here. Again, this one is probably a little bit more mathy than the other ones, in the sense that, like, I'm not looking at a specific, you know, application of it, but I'm just trying to find points on a curve that are closest to the origin. All right. So let's take a look at setting this one up. So example 6 says, find the points on the curve y equals x squared minus 1 that are closest to the origin. So let's go ahead and start with a diagram. All right, x squared minus 1 is a graph that we should all feel confident sketching without the aid of a graphing tool. So if you graph this function, y equals x squared minus 1, what shape do we get?
Parabola facing up
Yeah, parabola facing up, and where
at
is
the
it?
-1.
Yeah, the vertex is going to be shifted down 1. Okay, so that means that I've got this point right here, and I can sort of sketch the rest of the parabola like this. And that 1 point I know is going to be 0, comma, -1. Okay. All right, so we've got our diagram. I'm going to add in the origin. So I know that I'm trying to find the points that are closest to the origin here. All right, so let's go on to step 2. So step 2 says I need to write an equation that is going to help me find out how far a point on this curve is from the origin. So what are our ideas on this? Any ideas on formulas here?
When you do the slope formula,
What would the slope formula help us find?
maybe like the x and the y. Or,
How would that help us find the x and the y?
I don't know.
Well, the slope would just be the derivative.
Slope would be the derivative.
Professor?
Yeah.
Would you just find, I mean, if you look at the origin and then kind of look beneath it where 0, -1 is, it kind of makes like a little circle. So I guess you could find use a radius formula somehow and then go from there, or of a circle, I mean.
Okay, you can't, that's not a circle. There's not a half circle down there. All right. So one formula that I think also comes up pretty often is the idea of distance. And so if we're thinking about points that are closest together, the distance between those points is at a minimum. Okay, so I'm going to add that on to the end of this problem, that closest to the origin. Another way we could say that is that the distance between the points, distance is a minimum. Okay, so closest to the origin means everything on that parabola, we want to find which one has the closest distance to the origin. All right. So the distance formula is probably a good one to remember. But if you don't remember it, the distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. So now let's maybe fill in some points that we know. So we want to find the points that are not just closest to any random point, but specifically closest to the origin. And the coordinates of the origin are 0, 0. And so what that means is for this x1, I can put in a 0, and for this y1, I can put in a 0. And so that's going to give me the square root of x2 squared plus y2 squared. Okay, because I replaced x1, y1 with the coordinate of the origin, which was 0, 0. Now, I don't know which point is going to be the closest, or points are going to be the closest, so I have to keep everything with variables. But if I look at this side, it's pretty clear that I have a multivariable equation because I have x and I have y. So we need to get rid of either the x or the y. And though this problem makes us guess some other things, and we see y2, we can actually put x squared minus 1. So they're kind in that way that they actually give us the second equation. We don't need to go and construct it ourselves. And so what we can do is write this as the square root of x squared plus, everywhere I see the y, I'm going to put x squared minus squared. Okay, so again, this came from another way to say y. All right, So let's go ahead and see if we can simplify this equation before we take our derivative. Ew. Okay. So if I were to simplify this equation, what might be some things that I could do here?
Wouldn't you have to FOIL it out?
Okay, let's go ahead and do that. All right, so I think I FOILed that out correctly. And I also combined some like terms here. So all three terms came from the FOILing of x squared minus 1. And then I added this x squared with the minus 2x squared. Now, because I know that I'm going to be taking a derivative, it's to my benefit to write it in a way where I can see the power. Okay. Now, from here, I'm going to take a derivative. I'm going to set it equal to 0, and I'm going to solve for x. So my derivative is going to equal, what rule do we need to use to find this derivative? Or rules, because we need more than one.
Chain.
We're definitely in rule. And what other rule?
Power.
And power. Good job. So chain and power. Now, I feel like some of us out there still feel like, well, you should only have to use one rule for any given problem, and that is definitely not true, okay? So make sure that you are aware of all of the rules that you might need. So for chain rule, I'm going to get 1/4 minus x squared plus 1 to the negative 1/2 times the derivative of the inside, which is 4x cubed minus 2x. Now, again, because I'm thinking ahead and I know that I'm going to be setting this equal to 0, I actually want to write this as one big fraction. All right, so again, this is a step that I want you to be super, super familiar with, knowing how to go between positive and negative powers and fractional powers, and knowing how to write things, whether they go on the top or on the bottom, is a really, really important and fundamental skill. All right, so in this case, I think that we can go ahead and multiply the denominator to the other side, and that's going to give us 0 equals 4x cubed minus 2x. And I can begin to look at this like 0 equals 2x, and then I get 2x squared minus 1. So I want to start to think about factoring. I'm going to get 0 equals 2x, and this is actually going to be square root of 2x plus 1 and square root of 2x minus 1. Now, what that means is there are 3 potential solutions, okay? There are 3 potential solutions. So we need to take this first part and set it equal to 0 and solve for x. We need to take this second part set it equal to 0, solve for x. And we need to take the third part, set it equal to 0, and solve for x. So in the first one, we're going to get x equals 0. In the second one, we will get negative 1 over root 2. And in the third one, we will get 1 over root 2. Okay? Now, with these three options, we kind of need to go back again and see, do they all make sense given our graph? Okay? So let's see what we have. This first one, x equals 0. At x equals 0, that would mean they're talking about the vertex. Okay. And what's the difference between the vertex and the origin? Like, how far apart are they?
One unit.
Yeah, it's just 1 unit apart, right? I just count down 1. Okay. So then these other 2 points, let's turn this into a decimal, and let's turn this into a decimal so that we can visualize it a little bit better. So 1 divided by root 2 is going to give me a 0.707 or negative, and this will be a positive 0.707. So if I go back up to my graph, x values of positive and negative 0.7 would be like here and here. Okay. So when we look at those are going to be the ones that give us the maximum, or sorry, the minimum distance between the curve that we have and that x, the origin. All right. So folks, that's our last example for today. There are, I think, let me take a look. There are 6 more examples in that extra practice on Canvas, and then there are some questions like these in your homework on WebAssign. So those are all options that you can use to get started in your own personal practice on this. And again, I think that it's reasonable to listen to someone else do them and be like, oh yeah, I get these steps, like why she did this, but it's a different feeling to try and do it on your own and think, okay, could I think of that next step by myself? All right. And so that's really where I want us all to be, is like, yeah, okay, I have a clear understanding of how to do this. And if the formulas for step 2 are my downfall, then I make sure that I show all of those formulas on my cheat sheet for the final. Okay. So make sure that you are taking the steps that you need to take to make sure that you are setting yourself up to be successful on that final exam. All right, so I'm going to go ahead and stop sharing my screen and back into the Zoom room. And Diana, if you want to stop the video, I think now is a totally fine time to do